All right, so we're going to finish up on chapter 11. So we're going to look at sequences today, and we're going to look at a series tomorrow, the next 2 academic days that we have class. So the idea of a sequence is it's a list of numbers. That's all it is, just a list of numbers. And the goal is to try to find a pattern. Once we can figure out that there is a pattern to the list of numbers, we can usually come up with a formula to predict the numbers. The reason that a formula is helpful is because if I said I want to find like the 7,000th term in the sequence, well, if the pattern was just adding 2 each time, you could maybe figure out a way like, all right, I got to add 2, 500 more times, so that really is going to add 1,000, and you could kind of figure out the number that way. But if the pattern is complicated, we would like a simple way to figure out any term that we want to know and find it very quickly. The idea of a series, which we're going to look at tomorrow and Wednesday, is when you add up all the numbers in a sequence. Okay. But for today, we're not adding them up. We're just actually finding the individual terms. Tomorrow, we'll look at adding them up. So this particular sequence is called sequence B. Generally, a sequence is named with a lowercase letter. And the subscript is there to indicate the term position. So B sub 1 is the first term in sequence B. B sub 2, second term. Okay, B sub 78 would be the 78th term. When you put ... in between like that, that means there's more terms in between, but it does stop. The way that you know a sequence stops and it doesn't go on forever is where the ... is. If I put another ... at the end, now that's a sequence that goes on forever. That's a sequence that stops. We don't know where. Maybe it stops after 10 more terms, or maybe it stops after 100 million terms. Right? But it does stop. So in order for a sequence to be unique, there has to be a rule to calculate the terms in that sequence. Now, you can actually do a lot of neat things with sequences. You can, if you know a sequence, there's a website you can go to. You can pull up the sequence on the website, and it can map the sequence to like musical notes. So it's kind of neat sometimes if you can hear a sequence. Sometimes it doesn't sound like anything, but sometimes you hear like a pattern in the notes. So if we have time after, I can try to show you that website. The problem is the website generates the sound file in like a really old format, so I have to like convert it. It's like a few steps, but it's still kind of neat. All right, so let's look at this sequence. Okay, this particular sequence is an infinite sequence. It does go on forever. And I would say if you have the first 3 or 4 terms in a sequence, that should be enough information to point you in the direction of a formula for it. All right, so let's see if we can figure out a formula for the nth term in that sequence. Anyone think they notice a pattern with 2, 5, 8, 11? Yeah?
Adding 3 every time.
All right, can you be more specific about what you're adding 3 to?
The previous term.
The previous term, yes. So if that is the current term, how do you think you would write the one before that?
You need to go back up.
A to the n minus 1 plus 3.
Yeah, a sub n minus 1. So it's a
sub n minus 1.
Yeah. Yep. So this means the previous term. Whenever you subtract 1 from a position, you get the 1 before it. And then plus 3 means that's the pattern we noticed. So that's the formula for that sequence. It's one way to write the formula. So now, let's say I wanted to know the 440th term. Using the notation above, what would be the formula for the 440th term? Yeah? Yeah.
A sub 440 minus 1 plus 3,
So, and what's 440 minus 1?
439.
So it's the 439th term plus 3. That's how you find the 440th term. Take the one before it and add 3. Okay, now, do I know the 439th term right now? Cool. What do you think? No, we don't know the 439th term. So now we got to figure that one out. What's the formula for the 439th term? Yeah.
A sub 438 plus 3.
A sub 438 plus 3. We're going to be here a while, right? This is going to take a long time to figure out the 440th term doing it that way. Because you have to figure out every single term up to that one. It's doable, especially for a computer, but it's not the most efficient way to find the nth term. So let's think about a different way to find the nth term. Instead of thinking of what you do to the previous term, I want to think of what you're doing to that number that I just wrote in purple. That number in purple is the position of the term. So is there something you can do to the position of the term to turn it into an 8? Or somehow to turn a 4 into an 11? Yeah?
You can change A to, or A1, which would be 2, then plus the pattern N to, or pattern N. So it's basically the first term, which would be 2, plus the pattern, and then whichever pattern you're trying to find.
So I'm looking. So I would like something in this box that I can fill in 4 into the formula, and the calculation comes out to 11.
So it would be 2 plus 3, and then subscript 4.
Well, it's got to have a variable in there somewhere because we're calculating the nth term.
Or 3n rather than 4.
All right. So let me.
Minus 1.
So what do you think it is?
2 plus 3 subscript n minus 1.
You're close. You're pretty close. Yep.
2 plus 3 parenthesis n minus 1 closing parenthesis.
2 plus.
3 open parenthesis and minus 1 closing parenthesis.
All right. Let's see. Let's see if that works. I'll just put that down in the box. Let's plug in 4 and see what happens. 4 minus 1 is 3. 3 times 3 is 9. 9 plus 2 gives you 11. All right. Let's plug in 3. 3 minus 1 is 2. 2 times 3 is 6. 6 plus 2 is 8. So yes, that formula does work. So now, if you wanted to find the 440th formula, or 440th term, all you have to do is take 440 and plug it in right there, and it's very fast. It's going to be 339 times 3, whatever that is, plus 2. So it's a very, very quick way to find that term. This type of formula on the right is called explicit. The one on the left is called recursive. Recursive is generally easier to figure out, not as useful. Explicit is a little bit harder to figure it out, but it's much more useful. Okay? And we're going to talk about a way that you could figure out that formula if you're not sure how to do that in kind of a methodical way. So I'm going to show you that. And you could also simplify this to 3n minus 1, okay, if you distributed that out. So if you triple that number and minus 1 from it, you will always get that number. I just wanted to see if people could figure it out before we went over how to do it, and it looks like we were able to figure it out. Now, when you're using one of those formulas, okay, you can go back to that second formula. When you fill in something for n, okay, we're used to working with real numbers a lot. Positives, negatives, fractions, decimals. You can plug in anything you want. When you're dealing with a sequence, that's not true. N represents a position. Okay, think of like a position in a race. Okay? You can finish first place, you can finish second place. So you could plug in a 1, or you could plug in a 2. You can't plug in 1.3. There's no such thing as finishing in 1.3 place. Right? There's no such thing as finishing in negative 5th place. Right? There's also no such thing as finishing in 0th place. That doesn't make sense either. So the formulas that we're going to be using only allow you to plug in integers, positive integers. 1, 2, 3, 4, 5. So counting numbers.
Natural numbers.
Yep. So the domain of every formula that we come up with today is just counting numbers. That's it. And how high do the counting numbers go? Well, it depends on how many terms in your sequence. They can go as high as you want. So I talked about 2 different kinds of sequences, and if you have a dot, 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 that tells you if it's infinite or finite. So an infinite sequence goes on forever. When you see it written, you can have a dot, dot, dot at the end. When you write down a formula for an infinite sequence, the domain of the formula is every single positive integer you can think of. You can plug in anything you want that's a positive integer. When you're dealing with a finite sequence, the domain of your formula is not all positive integers. It's from 1 up to however many integers are in your sequence. Could be 100, could be 1,000, however many you have. Okay, so any question on the difference between infinite and finite? And we're going to come back to the idea of infinite and finite when we start adding up all the numbers in a sequence. If you have a finite sequence and you want to add up all the numbers, well, that's easy. Even if there's 10 billion numbers in the sequence, you can still add up 10 billion numbers. Right? You can do it. When we get to an infinite sequence, you might think at first, how can you add up infinitely many numbers? Like if you never stop adding numbers to something, won't it just get like bigger and bigger? And the answer is it depends. Right? So we'll talk more about adding up infinitely many things later on. And that's something that you can't do directly. Right? You can't spend the rest of your life adding numbers up, right? Infinity. It's going to take a long time. So we've got to come up with a way to think about that. And we will. All right, so here's an example where they're just giving you a formula, and they want you to find the first 3 terms and then the 15th term. This type of formula is the one that's harder to come up with, but it makes finding the terms very easy. All right. So if I want to find the first term in the sequence, what number would I plug in for n? 1. Yeah, we're going to plug in 1. If we plug in 1 in the numerator, we're going to get 0 over 1, which tells me my first term is 0. Yep. Now, if you get a negative there, that's fine. You can have a negative value. Right? You can't have a negative position. 1 is the first position. Right, Dex, what would I plug in to find my second term? 2. And if I plug in 2, what do I get in the numerator?
3.
I get 3, and in the denominator, I get 2. And there we go, so 3/2. Nick, how about to find my third term?
3.
3, and what are we gonna get as a fraction when I do my third term?
8 over 3.
8 over 3. And Holly, to do my 15th term, we can jump right to it. We don't have to find the 4th, the 5th, the 6th, and so on. What would you plug in to do the 15th term?
15.
Yep, 15. And what do you get in the numerator if you plug in 15?
224.
224. And denominator?
15.
15. Hey, and that's it. There's the first 3 terms and the 15th term. If you start to divide those out and look at the decimals, you would start to notice a pattern. And the pattern is that the value of what's in this box is getting closer and closer to that number. But it's always going to be off a little bit because it's -1. If that -1 wasn't there, let's see, what's n squared divided by n?
And
N, right? You get exactly this. But because you're minusing 1 from the top, it's going to make the top just a little bit different. So when you divide it, it's always going to be a little bit lower than that number. So this is probably like 14.99 or something. Okay. Let's look at I had one more. There we go. Let's look at this one. Okay. Anyone notice what's going to happen in this sequence? Yep.
it's an alternating sequence, so
Yep.
it is negative on odd integers or odd numbers and even on even, or not positive on even numbers for n.
Yeah, yeah. So this is called an alternating sequence. Whenever you have a -1 to the n, the -1 to a power doesn't actually change. Well, it doesn't cause you to multiply anything by other than 1 or -1. That's what this does. So in other words, it alternates it between positives and negatives. So if we plug in 1, we're going to get -1 to the 1 times 2 to the 1, which gives you -2. So that's the first term in this sequence. How about my second term? If I plug in 2 for n, what's my second term? Yeah?
4.
It's going to be 4. What about my third? If I plug in 3, what's my third term? Yeah? -8. So what's happening is it's doubling each time, but it's also changing sign. Okay, 15th term. Positive or negative? Yep.
Negative.
It's going to be negative because negative number to an odd power is always a negative. And now we just have to figure out 2 to the 15th power. Let's see, like this. 2 to the 15th power is 32,768. There you go. There's the first 3 terms and the 15th term of that sequence. So any questions on how to calculate terms if I give you a formula? Okay. So now, if we wanted to think about graphing a sequence, okay, this is the formula that we just did. So let's graph it. It was the n squared minus 1 over n. I think the first term was 0. Second term was, what was that, 3 over 2. Third term was 8 over 3. And let's let's do the fourth term just so we can get one more point on here. Fourth term is going to be 15 over 4. Okay, so it's going to be a little easier if I change into decimals when I want to graph it. 8/3, what's that? 2 2/3, so 2.67. 15/4 is what? 3 3/4. Okay, and let's graph it. Now, when you graph it, remember, you can't connect anything because there's nothing between the first term and the second term. So we're going to graph position and then the value. So first position has a value of 0. Okay, so 1, 0. Second position has a value of 1.5. Third position, 2.67. 1, 2, 3. And notice each time the dot is getting a little bit closer to the line above it. Right? The difference between the decimal and the next integer is going to keep getting closer and closer and closer. 3.75. 4, 1, 2, 3. Right up there. Let me zoom in on that a little bit. So that's a picture of what your sequence looks like. But don't connect them because there is nothing in between the first and second or second and third terms. So any question on graphing a sequence? The graph is always the position, comma, the value in that position. All right, so the formulas that I gave you for the last two, the alternating sequence and the one we just graphed, those were called explicit. An explicit formula, if you're trying to find one, that's the best one to find. Okay? It allows you to find any term you want right away. The other type is recursive. Okay, again, recursive, easier to figure out, not as useful. So in a recursive formula, I have to give you the first term, or maybe the first couple. And then the formula is based off the previous term. Okay, we don't get into any formulas that are that hard, really. They're not too complicated. Usually the formula is either going to be adding or subtracting something from the previous term or multiplying the previous term. Okay? But in general, they can get pretty hard. Right? Like if I gave you a formula that said, to find the next term, take the previous term, square it, double it, and then subtract 17. All right? That would be a really hard formula to figure out. Explicitly. Okay. Question?
I was just asking you if you want to.
Oh, yeah. So what we're going to try to do is if we come up with a recursive formula, we're going to try to convert it to explicit. And if all you're doing is adding or multiplying, it's pretty easy. But I'm going to show you a formula that I think you've probably seen before. It's a pretty famous recursive formula, but the explicit formula for it is pretty advanced. Okay, so the key with recursive is they have to give you the first term. If they don't start you off with the first term, then you can't do anything. So let's try this one. So this is similar to the last example. I just want you to list the first three terms, but I've defined it recursively. So what does that mean to do? Like if you had to explain that to somebody that doesn't understand all that notation, just in English, what is that rule telling me to do? To get the next term, I do what? Yeah?
Add 3 to the previous term.
Yep, add 3 to the one that comes before it. That's all it says. So my first term is a 2. Why is it a 2? That's given. That's just given. What would be my second term based on that rule? Amanda? What would be my second term?
4.
All right, what's the rule here?
The rule is a sub n minus 1 plus 3.
And yeah, what does that mean in like simple language?
That to get the next sequence, or like the next number that you would add 3 to the number before.
Yeah, add 3 to the one that comes before. So if we have 2 and we add 3,
Sorry, what?
so if
Sorry, I said that.
we're at 2
Yeah,
and we're trying to get the next term,
yeah.
and the rule is to add 3.
So 5.
Yeah. Okay. So add 5.
I don't even know any wins.
So yeah, that's the second term. How about the third term? It's going to be my third term. What is this? 8. Okay, so 2, 5, 8. Now, if you wanted to go all the way up to 600, well, you need to figure out, all right, well, I've got 500 and something more terms to go. I got to add 3 that many more times. Then you got to figure it out. So recursive, not as useful. But that's how you list the terms in a recursive sequence. All right, here's another one. It says determine the first 4 terms and the 8th term of the sequence defined below. Okay. What's the first term in this sequence? James, what's the first term in this sequence? 2. How do you know that? It's given, yeah. If we have a recursive formula, it's got to be given. And the rule says to add 4 to the term that comes before the one you're looking for. Okay. So what would my second term be? Yeah, 6. Okay, so they wanted the second term. And third term? Yeah, 10. And the fourth term? Yeah, 14. Now, they want the first 4, and then they want us to jump to the 8th. Well, with a recursive formula, there is no way to just fill in like an 8 and then get that directly. We got to find all the ones leading up to it. Okay. So the next one is going to be 18, 22, 26, and now we can get the one they want. Okay, so a couple problems with recursive. 1, it can take a long time. 2, it's very easy to make a mistake. Because if you're calculating all the way up to the 8th term and you make a mistake anywhere in the 5th, 6th, or 7th, your 8th term is going to be wrong. Any questions on how we calculated those terms recursively? Okay. So let's see if we can start with a recursive formula and then come up with an explicit one. There is a way to do this very methodically, but I just want to put it up and see if somebody can figure it out without me showing you anything. So the easiest way to do it is to list out the first 3 or 4. Okay? If you don't have a methodical way to do it, you're just trying to look at it and basically take an educated guess. List out, let's do the first 4. Okay, so my first term is 3.
Please go back up and down. Finish writing.
Based on this formula, what's my second term? Yeah.
It's 8.
Yep, second term is going to be 8. My third term is going to be how much? Oh, Waylon, what's my third term?
Is it
13? Yep, and Cole, my fourth term?
18.
18. Okay, so the goal is to figure out a formula that you can plug that number into and end up with that number. Anyone think they see a formula and if you think, well, maybe just times 4? Well, it works for that one. 2 times 4 is 8. But 1 times 4 is not 3. So it's got to be a formula that works for all of them. Anyone? Yep.
Could you start with like the first term and then add what you're increasing by and multiply that by n minus 1?
Okay, so you said the first term and then add how much?
I mean like the first term, which is 3.
Oh, 3. I'm sorry, I wrote that wrong. Yeah. I thought, yeah. So 3
plus 5 times in parentheses n minus 1.
Okay, and let's simplify that just and see what happens. So that's 5n minus 5 plus 3. So 5n minus 2. That's the simplified version of what you just told me. So let's see if multiplying by 5 and minusing 2 works. 3 times 5 is 15. Minus 2 is 13. Yep. 4 times 5 is 20. 20 take away 2 is 18. Yes. So we have found it. That is the formula. And that's called an explicit formula. So when you write it the way Holly did the first time, we can see it does have something to do with the first term. And then it has something to do with what you added each time. And then we take that and we simplify it as much as we can. But if you know how to do it this top way, that's pretty much the setup every time. It's the first term, what you added each time, and then an n minus 1. Okay, let's look at this one. So this is the sequence I said earlier. It's a pretty well-known recursive sequence. Sometimes they put these numbers on the back of paintings in an escape room, but they're really high numbers, so you don't recognize that it's a Fibonacci sequence, and you fail to figure out the puzzle even though you're a math teacher. I'm just saying.
This feels like a personal window.
So in a Fibonacci sequence, generally the first 2 numbers are 1 and 1. And then the pattern is you add each of the previous 2 terms together. So this is a formula that relies on the previous 2 terms added together. So we have a 1 and a 1. What would be the next term in my Fibonacci sequence?
2.
Yep, it would be a 2. And then the next one?
3.
1 plus 2 is 3.
5.
And then 2
And
plus
then
3
we
is.
have 8.
And I think we've got the first 6.
13. Oh, that's wacky.
Okay? So that's the Fibonacci. See, if you want to do one more, it'd be 13. Okay, that's the Fibonacci sequence. Now, to figure out a formula, to say figure out the 25th Fibonacci sequence, Fibonacci number. Well, that's the first position, second, third, fourth. You're going to have a hard time figuring that out. Okay, something you can do to a 5 to turn it into a 3. Something you can do to 7 to turn it into 13. It is not as simple as like adding or multiplying. There's a lot more to it. Or squaring and square rooting. There's a lot to it. All right, so it's not something that we talk about. But there is a formula to do. So that's a Fibonacci sequence. So when you have a recursive sequence, you can have it depend on as many terms as you want. I could have it depend on 10 terms. Right? So to get the 11th term, I have to do something to 10 terms before. Maybe I take the first term and double it, and then add the second term squared, and then subtract 5 times the third term. I can make it really complicated. All right. Any question on the Fibonacci sequence? All right. So another place that you see the Fibonacci sequence is in this triangle. This triangle has a special name.
Pascal's triangle.
Yep, it's called Pascal's triangle. And the way that it works is to get this number, you add the 2 that are right above it. So like 1 plus 7 gives you 8. The numbers on the edge are always 1s. So you have 1s on the edge, start with a 1 on the top, and then to get any number, take the 2 and add the ones that are above it. This triangle is used, there's all kinds of different patterns that come up here. I'm going to show you how the Fibonacci numbers come up here. But one pattern you'll notice is that if you look at a row that is prime, okay? Look at a row that has a prime number. Every number in the middle of that row is a multiple of that number. So like this is row 5. All the numbers in the middle are multiples of 5. The next prime number after 5 is a 7. All the numbers in the middle of row 7 are multiples of 7. That doesn't work for non-prime rows. Like if you look at row 8, not every number in the middle of row 8 is a multiple of 8. Okay, but it would work for 11.
Or 4. 4 is
Yeah.
probably-
So that's a pattern that comes up. Another thing that this is useful for is if you are trying to figure out certain things in statistics. So like let's say I had 3 different objects, and I wanted to know how many ways could you choose 2 of these 3. Like you could pick, the red and the black one. You could pick, both the black one. There's different ways you can do it, and this chart tells you how to figure it out. Right? It tells you how many different ways you can choose 2 objects out of 3 total objects. That would have been section 11.3, which we're not going to do. But let me show you where the prime numbers come up. So prime numbers have something to do with those diagonals. Oops. I just want to erase. I guess I'll do it like this. And if you take these diagonals, I've drawn them so they're at the same slope as the one of the sides in the hexagon. And if you put them right there, let's see, did I line them up right?
Some.
Okay, we should see the Fibonacci numbers. So, you know what? I think I got them one off. Let me put let's see. Let's check that. So look at the first red slash. It goes through the number 1. So we got a 1. The second one goes right through 1 again. When I say goes through, I mean it goes through the middle of the hexagon, not the border. Okay. The next one goes through a 1 and a 1. The next one is 1 and 2, and if you add those together, you get a 3. The next one is 1, 3, 1, and if you add 1, 3, and 1 together, you get a 5. Let's see if the next one comes out to an 8. What's 1 plus 4 plus 3? Gives you 8. And the next one, 1 plus 5 plus 6 plus 1. 1 plus 5 is 6. What's 6 plus 6? 12 plus 1. 13. And there's your 13. So it's just a pattern. If you draw those diagonals in and you add up the numbers on the diagonals, it will tell you the Fibonacci sequence. All kinds of patterns with that. All right, so the last 2 sequences we're going to look at are what's called an arithmetic and geometric sequence. You can also call it a progression. Progression and sequence is the same thing. Now, I say arithmetic. I say arithmetic when I'm talking about like 1 plus 2. I call that arithmetic. Different people say it different ways. Yeah, you can say it either way. In an arithmetic sequence, this is the type of sequence where you are adding something to the term that comes before. So arithmetic sequence is adding the same number over and over. That's an arithmetic sequence. 3, 5, 7, 9, 11. Now, the number that you add to the one that came before, they call it D. Anybody know why they call it D? I'll give you a hint. D stands for difference, common difference. Why would something you're adding over and over be called a common difference? Yep.
Subtract one term and the next term.
Can you be more specific about how to do that?
Subtract subtract n minus 1 of a subscript n minus 1 and from a subscript n.
Yes. If you subtract the term and the one that came before it, you will get what you're adding each time. So if you're not sure how to figure out, like if you're looking at 3, 5, 7, 9, 11, and you're like, oh, I'm not sure what you're adding each time, well, do 5 minus 3, and you get a difference of 2. 7 minus 5, 2. 9 minus 7, 2. There's a common difference of 2 if you do that subtraction. And if you can figure out that common difference, and you can figure out the first term, those are the only two things you need to know to come up with a formula. So now we're not going to have to try to look at it and just guess. Like, all right, is it times 4 and then minus 6, or is it times 3 and then plus 2? If you know those two things, the formula is automatic. So this is the explicit formula for an arithmetic sequence. It's the first term plus n minus 1 times d. And I want to make sure we remember, what are you allowed to fill in for n? Because this formula is in the context of a sequence. I mean, yes, technically you could plug in anything, but in the context of a sequence, positive integers. Perfect. Positive integers. Yep. All right. So now let me give you a few problems where I give you enough information that you can figure out the first term, and you can figure out what you're adding each time. And then we'll write the formula. When you write it, always reduce it as much as you can. Okay? So that means if there's a distributive property, do it. Okay. I had to add something to that problem because I did not give you the first term. So if I don't give you the first term and there's no way to figure it out, then you can't do that. Okay, so now looking at what I've written, identify the first term, identify what you're adding each time, and then fill them into the formula. Okay. What's my first term? first term is 5. And somebody else tell me, what am I adding each time? Yeah, 3. So first term is 5. The common difference is 3. Now, fill those in and see if it works. So we're going to get 5 plus n minus 1 times d. Okay. What do I get when that's as simplified as much as possible? Yeah.
3n plus 2.
3n plus 2. Now let's check it for a couple terms and see if it works. First term is 5, then 8, and then 11. I just did those by adding 3 each time. Now I'm going to check it with my formula. If I plug in a 1, I get 3 times 1 plus 2 is 5. If I plug in 2, 3 times 2 is 6, plus 2 is 8. And if I plug in 3, 3 times 3 is 9, 9 plus 2 is 11. So yeah, it seems to work. Now, that doesn't prove it works. What if it works for the first 500 terms, and then I try the 501st term, and it doesn't work? Well, that is something that we're not going to quite get to. That would have been, I think, section 11.5, where we prove that that is the formula. Not just that it, we think it's the formula based on trying it a few times, but we can prove whether that is actually right or wrong. And you can't prove it by plugging in every single number, because there's infinitely many numbers you'd have to check it for. So there's a way to prove it. But for now, that's all we're going to do. Any question on that? Okay. Let's try this one. The first 2 terms in an arithmetic sequence are -8 and -2. Find the 5th term. Let's just say using a formula. And by formula, I mean the one I just showed you. Okay. So first, can somebody give me what my formula would be explicitly? You don't have to reduce it yet. We'll do that together, but I just want to know what would be my formula from the previous page. Well, Joe. Yeah. What would be my explicit formula for that sequence? Okay, can you give it to me not simplified so we can just see, and then we'll simplify it together?
-8 times n minus 1, or -8 plus 1.
-8
Minus 1 times 6.
plus n minus 1. Okay, yeah, looks good to me. And then when you simplified it, what did you say that came out to?
6n minus 14.
Perfect. Got it. So that's 6n minus 14. Now, find the 5th term. How do I use that formula to figure out the 5th term?
Plug in 5 for n.
Plug in 5 for n. Yep. So it's going to be 30 minus 14, which gives me a 5th term of how much? Yeah, 16. There you go. So there's your formula, there's your term. All right. Any questions on that one? Okay. What's different about this one? There's something here they did not give me.
All the first number.
They didn't give me the first term. Well, we've got to figure that out somehow. So how can I reason out what the first term would have to be based on what they gave me? Yeah.
Use recursive formula.
All right, so we could try to think recursively to figure out how we're getting from 13 to 3. Does anyone think they see the pattern of how you're getting from 13 to 3? Yeah?
You're subtracting 2 every time?
Yeah, if you just look at the difference between the two numbers, that's a difference of 10. And you have to get from 13 to 3, which is a difference of 10, in 1, 2, 3, 4, 5 jumps. So you have 10 units to travel, you have 5 jumps to do it in, each jump has to be equal, so you're subtracting 2 each time. Yep. So 11, 9, 7, 5. It's not really important that we go that way. What's more important is we figure out the first term. So based on that, what's my second term?
15.
Yep, 15. And then my first term. Yeah,
17.
there we go. Now we know the first term, and we know what we're subtracting each time. So my formula starts out with what? What's the first thing we put in the box? Yeah,
First term,
first term, which is
17.
17 plus, and what always goes in parentheses. This part never changes. Yeah, and minus 1. Well, it won't change until we distribute. And then what's going to be distributed to that on the outside? Yeah,
-2.
-2. Okay, so when we simplify, we're going to get -2n. And what's going to be my constant on the end of that? Yeah,
Plus 19.
plus 19. Okay, so that's how we can take information we're given and then convert it into an explicit formula for arithmetic. Any question before we look at the last type? Yeah,
So how is it plus 19?
because when you distribute, you get 2 and then plus 17. Okay, anything else on that one? All right, last type. Geometric. What do you, so the pattern last time was adding or subtracting each time. What do you think the operation is going to be this time? Yeah?
Multiplying by.
Multiply. Yeah, it's always going to, we're going to think of it as multiplying. If we want to do dividing, we'll just think of it as multiplying by a fraction, like 1/2 or something. So this type of sequence takes the previous term and it multiplies by a constant. So it's the previous term, a sub n minus 1, times a number. That number you multiply by each time is called r. So r is taking the place of d. There's no more common difference. R stands for common ratio. Why do you think r is called a ratio? Because usually ratio implies that you are dividing two things. But I said that you're multiplying each term by something to get the next one. So why do we call R a common ratio? Yeah.
To find it, you have to divide one term and then,
Yep, divide one
next
term.
and the next term to get the constant.
So we're going to take one term and divide by
The previous term.
previous term, yes. If you take any term and divide by the one that came immediately before it, that is the calculation for R. Right? So if you're not sure, Take a number, divide by the one that comes before it, and see if you get the same thing all the time. If you do, you have a geometric sequence. So that's how you calculate R.
Can you scroll back up?
And there's different ways you can say take a term and divide by the one that comes before it. This is fine. This is a term, and a sub n is the one right before it. I could have also done this. That's the same thing. Just take a term and divide by whatever comes before it. Right, and this is called a geometric sequence. So that is the formula you want to use for a geometric sequence. Still relies on two things, just like the other one. You need the first term, but you don't need D this time, you need R. So it's the first term and R. All right, so example 9 says find an explicit formula for the sequence. Did they give me the first term? What do you think, Waylon? Nope, so we're going to have to figure that out. Did they tell me what R is? Nope, they didn't tell me R either. So I'm going to have to figure that out. Okay. First thing you want to do is figure out R. To get from this to that has to be as you go left to right. You need to tell me what you do. How do you change -6 into 12? And if you might think, well, wait, couldn't it be adding a certain amount? Like, no, it can't be adding because it says geometric. So it tells you it's not. You're not adding to get to 12. Yep.
You multiply by -2.
Multiply by -2. So what we want to do is go back the other way to figure out the first term. So we know we multiply by -2 to go to the right. We can figure out how to go back. Yeah?
B3.
It's going to be 3. If you divide by -2, it'll bring you back the other way. Yep. Okay, so now we know the first term is 3. And we know what R is. So what is going to be my formula to calculate the nth term in this geometric sequence? How about Megan? What's going to be the first thing inside the box? Not sure? Well, look at the formula on the left-hand side where it says explicit formula for a geometric sequence. And what does it say the first thing you write down is in that formula?
The first term.
Mm-hmm.
So it would be 3.
And the first term is 3. Yep. So we're going to start with a 3. And then times. And what comes right after the first term? Yep.
R, which is
R,
going to be -2.
which in our case is -2. And what else do I need?
Power of n-1.
To the power of n-1. Yep. That's an n. And that's your formula. Let's try it for the third term and see if we get a 12. What's 3 minus 1? How much? Yep. 2. What's -2 squared? 4, and then times 3. 12. So if you plug in a 3, yeah, you get a 12. So that formula correctly predicts that term. Yep. All right. Any questions on that? All right. So that's a geometric sequence. So now, once we know how to find the terms in a sequence, then we can talk about, well, what if I continued this sequence to the 798th term? What would they all add up to? That's the next step, right? That's a little bit harder, but we can still figure that out pretty easily once we talk about some patterns that come up. All right, let me see. Fix that. So 1 through 13 odd, 14 is the only even question. And then 17 to 27 odd, and 31. Okay, so remember, tomorrow is the MCAS schedule. So we have class, I think it's in the afternoon. It's later than it is.
Yeah, that's the last two periods.
It's later than it is now, yeah. Okay, so I will see you guys tomorrow afternoon.